All right, everybody, welcome to chapter 8. Let's start getting through this, and by the end of this week, we should have quite a bit done, and we'll be through chapter 8, and then we'll move on to chapter 9. All right, so let's get started. So we're going to be talking, let's start by talking about types of chemical bonds. So we've been talking about ionic bonding. We've talked a little bit about covalent bonding. One we haven't talked about is metallic bonding. Okay, so in ionic compounds, you have an electrostatic or Coulombic attraction between positive ions and negative ions. So that positive and negative are going to attract, and these attractions are going to be stronger or weaker based on both the size of the charge, like a +1 and a -1 don't attract nearly as hard as a +2 and a -2. And then also it's going to be based on um, distance between the two ions, which will be based on ionic radius. We'll talk about that in a little bit. Usually in an ionic bond, what happens is an atom with a large electronegativity comes along and steals electrons from an atom with uh, lower electronegativity, usually metals, that readily give off electrons. Then you end up with a positive and negative, and then they attract. Covalent bonding is where two atoms share electrons. But you can have different types of covalent bonds. You can have polar covalent bonds, you can have non-polar covalent bonds. We'll talk about that. Your ionic bonds are going to be between metals and non-metals. Your covalent bonds will be between non-metal atoms. And then metallic bonding here, what you get is in your big block of metal, you have the positive nuclei of these metal atoms sitting in a lattice. And then what happens, and the reason metals conduct electricity so good, is the electrons will delocalize in a metal, and you'll get this sort of electron gas or fluid throughout it's a way to think about it, throughout the metal. And so all of these electrons are just kind of freely moving around. And that's a metallic bond. So the strength of a bond is given by bond energy. We're going to use bond energy to actually do some calculations. When we're talking about ionic compounds and ions are created, one thing we're going to look at is how, ba based off where they're at on the periodic table, we know what charge certain atoms are going to take when they become an ion. And you'll see that they actually, we use the language of they want to become, but that's anthropomorphizing atoms, but still, I guess it's as good an explanation as any. But they're going to become isoelectronic with their nearest noble gas. And so isoelectronic, remember, is they have identical electron configurations. The reason they go that way is because uh, your noble gases have completely filled valence shells. And a completely filled valence shell is very, very stable. So your ions are going to tend towards their nearest noble gas in their electron configuration. So here's a look at Coulomb's law. Coulomb's law is a force of attraction between two charges, or it could be force of repulsion. In this case, we're looking at force of attraction. That force of attraction is actually going to be the bond energy in the ionic system. And so see here you have your Q1 and Q2. That's the charge of the individual ion. And then your R is the distance between the two ions, which is going to have to do with ionic radius. And so you see we have ionic radius over here on the left. Um, what are some things about that? So you notice as an atom becomes a positive ion, the radius gets smaller. Well, if you think about that, when you remove electrons, uh, more of that positive nucleus is exposed to the remaining electrons, so it's going to grab those electron shells, pull them in tighter, making the ions smaller than the atom, versus when you add electrons to form the negative ions, you're adding more electron repulsion into various subshells or energy shells. And what those are going to do is those are going to then balloon up due to that electron repulsion. So your negative ions become larger than their constituent atoms. And this is all going to play a role. For covalent bonding, or the sharing of electrons between two atoms, so you have atoms come together, they're going to start sharing electrons, and then they're going to form this single molecule with a single electronic structure. But so in this case, the bond length is not going to have to do with the radii of, say, your like in ionic, it's the radii of your ions. But in this case, you end up with a bond length that minimizes the energy of the molecule. And so there's going to be a very specific bond length that's going to really balance out between, say, the repulsion of the positive nuclei, the attraction of the electrons in the bond. It's going to all come together and even out to a minimum energy bond length. And for all molecules, whether it's covalent or ionic bonding, they're trying to find a configuration that minimizes the energy of the molecule. So that's what they're all trying to do. And so we talked about covalent bonds being both polar and nonpolar. So every atom is going to have an electronegativity value. We talked about that in the last chapter. We can start to look at molecules via their polar bonds. And so there's two types of polarity we're going to look at. There's going to be bond polarity, and there's also going to be an overall polarity of a molecule. Some molecules have polar bonds, but the molecule itself is not polar. And we're going to be talking about dipoles. I think I defined that on another slide, but your dipoles are really, again, it's like, is your bond polar? Well, then that bond has a dipole. So one side's positive, the other side's negative. If you have a polar molecule, your molecule will have a region that's positive and a region that's negative. So that's the whole idea of a dipole. And we can start to really figure this out by looking at the two atoms involved in a bond, and we have a range here. So you see here we have a small list of electronegativities. You can find periodic tables that give the electronegativities of every atom. And when you take the difference, the delta electronegativity, so that's going to be you subtract the two and you get an overall difference between the two electronegativities. If you have a difference of 0 to zero point 0.4, your bond is nonpolar. Zero point 0.4 to 2.0, your bond is polar, and anything equal to or above 2.0, you have an ionic compound. So, like for example, let's here you see we have hydrogen fluoride at the very far left. And so if we say, well, what is the delta electronegativity there? So let's see, fluorine, 3.98, minus hydrogen is 2.20. That is going to give you a delta of 1.78, which you can see is very close to 2.0, but this is going to be in your polar region. So that is a polar bond. You could do the same thing with carbon and oxygen. Carbon and oxygen would give you a 0.89, which is still polar. So it's less polar, but it's still polar. Now we'll talk about these a little bit, but look around those molecules. You see these bubbles around them that show various color regions. These are in chemistry, these are called electrostatic potential maps. And they help you really figure out the polarity of a molecule because, again, one thing we'll cover in this chapter is molecular geometry. So the geometry of a molecule and the presence of polar bonds will either give you an overall polar molecule or it won't. And so these maps help you figure that out. So you're mostly worried about your red and your blue. Your red is going to be your negative region. Your blue is going to be your positive region. So it's like if you look at hydrogen fluoride, you're going to have your partially positive region at hydrogen, your partially negative region at fluorine, and I'll go ahead and draw the dipole in here, but we'll talk about it more. So your molecule has an overall dipole. Let's try to make that cleaner. Pointing along the bond. And so again, dipoles are just showing this is a polar molecule. The way you set them up is that little crossed region of the dipole goes at the positive end and it points towards the negative end. But it's like, let's look at, so this is a polar molecule because there's only the one bond dipole. But let's look at carbon dioxide. It has two bond dipoles. And so you're going to have a delta negative here, delta negative here. Your carbon is two delta positive for each of the delta negatives. And again, you don't have to get a number for the delta. It just means that's your partially positive region or partially negative region. So, but I have a bond dipole pointing that way and one pointing that way. And you can notice with those two bond dipoles pointing in opposite directions, and they're both the exact same kind of bond, you can see that those two are going to cancel each other out. And so carbon dioxide is overall a nonpolar molecule, even though it has two polar bonds. And water, if we look at that up here, so okay, your hydrogens, each one is going to be a delta positive. Up here, your two delta negative, and your bond dipoles are going to point along the bonds. And you notice how you have two bond dipoles that is, both of them point up a little bit. And so we're going to talk about this. So this is an overall polar molecule because these two, based off the orientation, the geometry of water, these two are not going to completely cancel each other out. So we're not going to go through all of vector mathematics, but you can actually figure this out thinking of these as vectors. But I want you to get used to more looking at molecules, seeing their geometry and their symmetry, and saying, okay, well, that one's going to be polar versus that one's not. So we'll work on that. Again, you can see by the symmetry, carbon dioxide, its bonds will cancel out versus water, its bonds will not cancel each other out. So again, electronegativity is the ability of an atom to pull electrons towards itself in a bond. Some electronegativity differences are so great that one atom completely strips electrons from the other one, forming positive and negative ions that will then attract via electrostatic attraction. So that'll be your ionic bond. In polar bonds, you'll have one atom that's so electronegative it pulls the majority of electrons towards itself. That's where you start to get your delta negative regions, your delta positive regions. So this is going to be based on electronegativity. It was kind of a historical thing, we have Linus Pauling who gave us a way to kind of to start to understand electronegativity through bond energy. So here, let's say you have a molecule that's going to be H bonded to some other atom X. So it's like hydrogen chloride or hydrogen fluoride. And so you have the bond energy of the H2 bond of an H2 molecule. You have the bond energy of let's say it's chlorine, of a Cl2 molecule. Those two are going to be broken. You have those two bond energies divided by two, which gives you an average bond energy. And so then when you calculate that, that's going to give you the expected bond energy of your hydrogen chloride. And then the delta, the difference in the bond energy is going to be your actual bond energy subtract minus your expected bond energy. And that delta bond energy is going to give you a measure of your electronegativity across the bond. And so then you can kind of go back to the scale we talked about on is this a polar or a nonpolar or an ionic bond? So let's look at some bonds. Which bond is expected to be the most polar and which is the purest covalent? So purest, the least polar. So a completely pure covalent bond would be like in the molecule O2, where both atoms are oxygen, so they have an equal electronegativity, and your delta electronegativity is zero. That's like that would be considered a perfect sharing of the electrons. Okay, so I'm gonna write down some electronegativities. Now I do this, yeah, you have them in the table to the left, but you won't always have that. Sometimes you have to look these things up, so it's good to make a list. Okay, so let's do the ON bond first. And this delta doesn't have to be in any particular order. The way I suggest doing it is just put the numbers in the way that's going to give you the positive answer, because you're not looking for positive or negative here. You're looking for a magnitude. Just how big is this delta? Okay, so that one is just on the line of covalent to polar covalent. Let's do sulfur nitrogen. So a little more polar than the previous one. Not a ton though. Oh, hang on. We are working on the phosphorus oxygen bond. Okay, now we're getting a nice polar bond. Now we'll do phosphorus nitrogen. Okay, still polar, not nearly as polar as the last one though. Let's see, phosphorus hydrogen. And that one's not polar at all. So when we look, we can say the least polar of all of these is the phosphorus hydrogen bond. So this is the purest covalent bond. That one has the most even electron sharing. And then here, our phosphorus oxygen bond is the most polar. Okay, so yeah, we could really use the activity numbers to start to figure out what's going on with the bond. Okay, so back to bond polarity and dipole moments. So, of course, your dipole moment is a measure of polarity, and it's going to be represented with the Greek letter mu. Okay, so let's start looking at some compounds with polar bonds. So, carbon monoxide. So when you look at the electronegativities of these, your oxygen will end up being your delta negative, your carbon will be your delta positive region. And so then, as we talked about, your dipole is going to point towards the negative, and you're going to get this. So this is your, and that's the both the bond dipole and the molecule dipole, because there's only the one bond in the molecule. Versus, let's look at water, where again, positive regions down here at hydrogen, 2 delta negative up at the water. Well, let's, so going from one hydrogen to, so we have a delta positive, delta positive, delta negative. So that's where we get the 2 delta negative. So then each one of these is going to have a bond dipole pointing towards the negative. But you can see that these two dipoles are not going to completely cancel each other out. So you get an overall molecular dipole, where again, now your bottom there where the hydrogens are, that's going to be your positive region. And when you look at the electrostatic potential map again, you'll see that that area is going to be blue versus versus up in the oxygen, you'll see red, which is uh, your your negative region. So that's the dipole points towards the negative. Let's look at some other molecules. So we have ammonia. Okay, so each hydrogen, because we check the electronegativity difference, so these are going to be polar bonds. Each hydrogen will be a positive. So that means that your nitrogen is going to have to be 3 delta negative. Now, each bond is going to have its own dipole. Okay. Now, let's try to think about this in terms of vectors. So let's just draw an XY. We'll draw our axes. We'll just call this vertical and this one horizontal. And then we can, each one of these is going to be pointing slightly up, because you can see the overall geometry of ammonia kind of looks like a three-sided pyramid. See, it's kind of like a pyramid. Kind of a new thing, trying to envision molecules in 3 dimensions. So that means that each one of these bond dipoles is going to slightly point up. Now, what this means is that this vector, okay, so this vector is going to have components. It's going to have components in the horizontal. It's going to have components in the vertical. And so if you're looking, let's deal with the horizontal first. If you find vectors existing pointing different, pointing equally in different directions in a perfect symmetry, they're all going to cancel each other out. So if you're looking straight down on the horizontal ones, what you're going to see is 3 equal. They're all nitrogen hydrogens. 3 equal horizontal vectors pointing equally in the different directions of a circular symmetry. Okay, so when you start breaking these down into their individual components, you will see, let's see, we'll call this 1, 2, and 3. 1 plus 2 plus 3. They're all gonna end up canceling each other out. So ammonia is not going to get any polarity contribution from its horizontal components. However, all of its vertical components are pointing up. Every single vertical component's pointing up. So that's going to be so essentially you could say this has a magnitude of 3 mu v. So since that's not 0, we have a polar molecule. And so if everything canceled out, we would have a nonpolar molecule, but that's not what happens. So we have, I'll just draw it through. So we have an overall polar molecule pointing up towards the apex of the pyramid. And again, you don't have to really, I'm just trying to show you how you can analyze this, but you can also just look at if you're more comfortable looking at the geometry of the molecule and saying, okay, well, I can see that all 3 of those bond dipoles point at least a little bit up. That means that these are not going to be able to cancel each other out completely. I know that ammonia is going to be an overall polar molecule. But we can go back to carbon dioxide. And of course, we said the oxygens are delta negative. You have a 2 delta positive for the carbon. So since that's the positive region, your dipoles are going to point towards your oxygens. Now you can see here we have 2 carbon-oxygen dipoles pointing the exact opposite direction. So they're equal and they're pointing the opposite direction. So you can see here. So since this molecule has dipoles pointing in a way that completely cancel each other out, this molecule is nonpolar, even though it has polar bonds. Let's look at some others. This one I think is going to be, I want you to practice with this one. This is called a tetrahedral. It'll make more sense as we get through this chapter, but this one is probably the most difficult to visualize. So here we have carbon tetrachloride. I didn't use methane because technically the CH bond is not, if you do the electronegativity difference, this does not really qualify. CH does not really qualify as a polar bond. It's not polar enough to really count. So we needed something that was, so I went with CCl4. Okay, and then I've tilted it. So if you look in the box here, I've tilted the tetrahedral to get the more traditional, the more traditional setup for it. And I think it really kind of helps because then each one of these is chlorine, and your carbon is in the center. Okay, so we are going to set some positives and negatives. Positive. This direction is positive. Down will be negative, and to the left will be negative. So that's just going to kind of help us analyze this. Okay, now I can tell you that carbon chlorine is a polar bond. So that means each one of these, and your chlorines, of course, are going to be your delta negatives, because they're the more electronegative element. Your carbon is going to be 4 delta positive. Okay. Now, each one of these bonds is going to have a dipole pointing from the negative region towards, oh, I did that backwards, didn't I? Let me do it again. You have to point towards the negative. Okay, so then these two up here will also have bond dipoles. Okay. So if we look at these top two chlorines, we can start to analyze this. So we have our carbon right in the center. Okay. Now let me move this real quick. I think in my notes I did things a little backwards, but that's okay. Oh, yes, I did. Okay. So let's just set carbon right at the center of our coordinates. And technically we have one bond dipole that goes off like this, and one that goes off like, well, try to get these as equal as possible. One like that. Okay, so each one of these is going to have a vertical and a horizontal. Okay, so we'll call this one 1, 2. Okay, so here is mu1 vertical, mu1 horizontal. There's horizontal 2, and there's vertical 2. And then when we look at these, okay, so our horizontals, so what we're going to get is horizontal 2 is pointing in the positive direction. Horizontal 1 is pointing in the negative direction. These are going to end up canceling each other out. Whereas our they're both pointing in the positive direction. Overall, this is going to give us 2 vertical dipole, basically a magnitude of 2 for our vertical dipole components. let's work on the bottom here. So now we have C again in the middle of a coordinate system. And now down, of course, is going to be negative. And then for the bottom two, we're going to have, let's move that. Okay, and this is also going to have horizontal and vertical components. And of course, again, you can see the horizontal, those are equal and opposite. They're going to cancel each other out. And so then when we get those are both negative because they're pointing down, we're going to get a -2 times our total, -2 times the vertical dipole moment. So when we end up adding these two together, we see that in the end, all the horizontal and all the vertical components end up canceling out. So since we get a total of 0 from all of our components, this tetrahedral shape is nonpolar. So these produce nonpolar molecules. Uh, Again, you can try to analyze this using vectors. Uh, Keep in mind there's a lot of vector math we haven't done, so I don't really expect you to do that. I'm just trying to show you a basic proof that these tetrahedral compounds are going to be nonpolar. But you could also think about it if you were to take a sphere and just wrap it around that molecule, and then put the bond dipoles in, you would see that those bond dipoles point off in equal directions in a spherically symmetric space, which should tell you that in the end they're all going to cancel each other out. No matter how many components you break them into, they're all going to cancel each other out. So again, when you have a symmetric molecule, oh no, because water's symmetric. But anyway, the point is these tetrahedral molecules are going to form non-polar molecules overall. It'll make more sense when we look at the electrostatic potential map. The last one I kind of want to look at is boron trichloride. Again, this one is a planar molecule. It's a triangle, and it's like a two-dimensional figure. All of those are in the same plane. So when we think about the bond dipoles, because again, we're going to have delta negatives and 3 delta positive. So that means each bond dipole, this one's easier to envision. And you were to look at these in a symmetric space, you only need a circle. So what you're getting is you're looking straight down, basically a triangle of vectors. And you can see that they're in a circular symmetric space. So they're all going to end up canceling each other out, and you're going to get this overall nonpolar molecule. Okay, so start wrapping your minds around the whole idea of the shape of a molecule and whether the molecule as a whole will be polar, even if you have polar bonds, because here again you see polar bonds, but the whole molecule itself is nonpolar based on its geometry. And this will really take some practice to get used to. So like this one is nice and symmetric inside of a circle, so those are all going to cancel out. This one is nice and symmetric inside of a sphere, so all of its bond dipoles will cancel out. Your carbon dioxide is symmetric along a straight line, but then we get to your ammonia, and you see you have that delta negative region sticking out into space with nothing to counteract it. So that one's going to be a polar molecule. In the water, again, you see your delta negative region sticking out into space with nothing to counteract it. So that'll be a polar molecule. And then we get to these electrostatic potential maps, and you can start to see how this maps out. So again, you can see the overall dipole of the ammonia. You can see equal regions of positive and negative for CO2. So that is overall nonpolar. Look at the reds. They cancel. If you imagine those pulling against each other, they cancel each other out. Look at the CCl4. You have all of your delta negative regions. Oh, that's bad. And they're all pointing in these various directions inside of a sphere. So they're all going to cancel each other out. So you have overall a nonpolar molecule, even though you have polar bonds. And water, of course, you have a delta negative region up here and a delta positive region down here. So again, you have an overall polar molecule. So polarity is kind of a different concept to get the first time you see it, but the more of these molecules that you see, the more it'll make sense. And in this chapter, we'll go through plenty of molecules and plenty of geometry. So the first thing you need to do is figure out if the bonds in the molecule count as polar. Do your difference in electronegativity, and then check does it fit into the polar region? And then start looking at the geometry of the molecule and saying, do these bond dipoles cancel each other out, or don't they? Okay, so looking at ions now. Now we've talked about ions and what their common charges will be based off their position in the periodic table. Here you see we have some group 1, group 2, group 17, 16, and 15. So you remember group 1 is a common charge of +1, group 2 is a common charge of +2, 17 is a common charge of -1, 16 is a common charge of -2, and 15 is a common charge of -3. Now, you'll notice in group 15, we only have the 2 atoms there. That's because below phosphorus, we start getting arsenic and antimony, which are metalloids. And if they go negative, yeah, they'll be -3, but they could be both, they can have the properties of both metals and nonmetals. And so if they display the properties of metals, then they can take on various positive charges. So we're really just kind of worried especially for your common charge, we're really worried about on the right side of the periodic table, your nonmetals, and then your groups 1 and group 2 metals on the left side of the periodic table. Now, we talked about atoms will take on will take on a charge. This is what causes the common charge, that they're going to take on an electron configuration that will be isoelectronic with their nearest neon gas. So groups 1 and 2, you're going to back up and find the noble gas. Is that what I said a while ago? Anyway, you'll find the noble gas closest to them is the one that's just behind them. And then for your right side of your table, your noble gases closest to them is the one that's to the right. So here, if you look at sodium, sodium has a 1s2, 2s2, 2p6, 3s1 electron configuration, with the 3s1 being the valence electron. Now, sodium will want to give up that electron in its valence and take on the 1s2, 2s2, 2p6 configuration, which is isoelectronic to neon. So you see now, how all of the valence shell for sodium is completely filled, and it takes on that same structure as neon because now its valence is the 2s2p level, and that's completely full, which is very stable. Calcium, of course, ends in a valence of 4s2, but when it backs up to its closest noble gas, you get an electron configuration that's isoelectronic with argon by losing those two electrons in the 4s valence shell of calcium. But your negative ions are going to go forward to their nearest noble gas. So here you see the valence of fluorine is a 2s2, 2p5. Where you see fluorine, let's do your 2s, 2p. You see this section, that spot right there is open to receive an electron, which is what will happen, filling up that valence shell and becoming isoelectronic with neon. Sulfur is a group 16 atom. So again, you end with a valence of 3s2, 3p4. So there's your 3p4, where you have two spots available to receive electrons, which is what's going to happen. It makes sulfur into sulfide, a -2, becoming isoelectronic with argon. And then nitrogen, you see your 2s, 2p valence. Your 2p is going to have three spots open to receive electrons, which is what it'll do, become a -3 and become isoelectronic with neon. So these common charge ions are really going to try to take the electron configuration of their closest noble gas. So, and we can use this knowledge to start predicting, what is going to be the formula for ionic compounds. And we've worked with this a little bit. And yeah, you can really do it based off the common charges. If you have a +2 and a -1, you're going to need two of the -1 anions to neutralize the +2 cation. But I don't know, let's start with sodium chloride. Okay, well, if you look at sodium, the sodium has its valence at 3s1, and it's going to want to give up that valence to then go back to be isoelectronic with neon and chlorine. That 3p5 has a spot open. Let's see. There's the 3s of sodium, 3s, 3p, 4, 5, and then there's a spot open right there. And so then, of course, chlorine is much more electronegative than sodium. So chlorine's going to really pull on sodium's one electron, and sodium will lose this electron over to here. And then sodium will be isoelectronic with neon. Chlorine, oh, what's that? Chlorine will be isoelectronic with argon, and now sodium will be a +1. With its valence shell full, chlorine will become chloride, will be a -1. With its valence shell full, and because you have a +1 and a -1, you will get sodium chloride, And you can look at that as a -1 and a +1, and those two neutralize. Okay, what about if we look at magnesium bromide? So I'm already showing you have your magnesium and your two bromides. Well, why is this the case? Magnesium's electron configuration. So magnesium's valence shell has two electrons to give away, whereas bromine if we look at the valence shell here, and remember your valence electrons are your 2 from 4s and your 5 from 4p. You have one spot open on bromine, but two electrons to give for magnesium. So for magnesium to give up both those electrons, it's going to need two bromines to fill up that 4p level. And so you're going to get the MgBr2. And then if we look at the charges on that, magnesium is a +2, bromine is two bromines is a -1 and -1. That's going to neutralize, so +2, -2. Let's look at rubidium nitride. Okay, so rubidium is going to have an electron configuration of krypton and then the 5s1 valence. So it has one electron to give away. Nitrogen, inner shell of helium, outer shell, 2s2, 2p3. So those has those 5 valence. And you notice 1, 2, 3 spots to fill up before nitrogen becomes nitride and becomes isoelectronic with neon. And so it's going to keep pulling on electrons till it fills those three spots. And that's why, since each rubidium only has one electron to give, you need 3 of them. And so you need 3 of them to fill up the one nitride. Also, again, you look at the periodic table, rubidium is in group 1. So it will become rubidium as a +1 ion. Nitrogen is a group 15. So its common charge is a 3 minus. And so again, if I think of it this way, I need all 3 of these rubidiums, each giving 1 electron. So that I can get a neutral molecule. And again, if we look at this, rubidium is +1, +1, +1. Nitrogen is a -3. So we do end up with a neutral molecule. So this is the way you can think of ionic compounds and what's going on inside of them, where electrons are coming from and where they're going to. So here's a question. What noble gas is isoelectronic? I don't know why it says as should, with the ions in the following compounds. So cesium sulfide, aluminum bromide. So what's cesium sulfide? Cesium is in group 1, so that's going to be a +1. Bromide, it's in group 17, so that's a -1. So that means I'm going to get, oh, cesium sulfide. Whoops. Sulfur's right there. That's group 15. Group 16. I'll get it here. Give me a minute. So that's going to be a 2-. So that means I need 2 of the cesiums to neutralize the 1 sulfide. Okay. So let's look at what happens. Cesium's configuration is xenon as your inner shell, 6s1, and it's going to lose that 1 electron. So it is isoelectronic, as you can see with xenon. Bromide, or that's the next sulfide. So sulfur is an inner shell of neon, 3s2, 3p4. It's going to want to fill up that n equals 3 valence level and become 3p6. So it's neon, 3s2, 3p6. And when that happens, that takes sulfur over to argon. So sulfide is isoelectronic with argon. Okay, now I can work with bromide. Aluminum bromide. Okay, so I look at the periodic table again. Aluminum's there. I remember the charge of aluminum is common at a +3. We've talked about that, so if you don't remember it now. Bromine is in group 17, so it's a common charge of -1. Bromide. So that means I need 3 of the bromides for the 1 aluminum. Okay. So let's look at aluminum. Okay, so we see 3 valence electrons, 3s2, 3p1. When it loses those 3 valence, becomes aluminum +3, the aluminum ion. It becomes isoelectronic with neon. And then your bromide. Start with bromine. It starts as argon, 4s2, 3d10, 4p5. It's going to want to gain 1 electron to become bromide. It's going to fill up its valence shell, which is 4s2, 4p6 now. And now that that's completely filled up, that takes me over to krypton. And so bromide is isoelectronic with krypton. Alrighty. So now we're going to talk about lattice energy. And remember, we talked about that's going to be based off Coulomb's law, which you see there at the top, and then the separation between the 2 ions. So here you see the radius of ion 1, the radius of ion 2, and the total. So then the total bond length between the 2 is that separation. So we can come to understand lattice energy. Here at the left, you see what's called a Born-Haber cycle. And so we know that the lattice energy is judged. It's calculated from where we have each of our constituent ions and their ionic phase and their ionic form gaseous phase. And so that your lattice energy is whatever that energy is from here to here. Okay, we can kind of look at that And we can see the magnitude going from here all the way up is going to be 411 plus 107 plus 496 plus 122. That gives us 1136 kilojoules. But then we notice here that we actually come down 349 kilojoules to the level we need to be at, and we need to know from there to there, which means that we can take 1136 minus 349. And so our lattice energy for sodium chloride is going to be a magnitude of 787 kilojoules per mole. But you notice that it's going down. So that's going to be a negative 787 kilojoules per mole. But there's two ways that we can actually get to this. We know the energies. So keep in mind here, this negative 411. Remember when we talked about formation equations? So that is the formation equation for sodium chloride. You start with remember we could only form 1 mole of the product we're looking for, and then we form it from the common forms of the elements that make up the compound. So in this case, solid sodium metal and chlorine gas. So go back and review formation equations. But we can actually figure this out two different ways with Hess's law. So we notice here in the Born-Haber cycle, we have a couple of things going on. These are the various, so you have the sodium phase change. So the atomization of sodium from solid metal to a gaseous form. The first ionization energy of sodium, so then sodium losing an electron. The atomization of the chlorine gas into individual chlorine atoms. And then the first electron affinity of chlorine to become chloride. So the only thing we don't really have is the lattice energy of sodium chloride, because we saw that the energy of formation, so the formation equation is a negative 411 kilojoules per mole. So we could do this two different ways. Let's say we're given that the lattice energy equation that we need has to be our individual ions in their gaseous form forms our crystal. And that's our lattice energy. We don't know what it is. So now we can use the individual parts of the Born-Haber cycle in Hess's law to figure out what lattice energy is. Okay, so what do we want? So we're trying to get from this equation to the overall formation equation. Okay, so let's put up the atomization, because that'll get rid of the sodium atoms. Okay, and then you get rid of the chlorides. Oh, that's the sodium ionization energy. We'll do the chlorine electron affinity. That's going to be a delta H of a negative 349 kilojoules per mole. Okay, now we have sodium and chlorine. Okay, we want to get rid of the chlorine gas, so we have the 1/2 Cl2. That delta H is 122 kilojoules per mole. Oh, I used a wrong phase. This one here is a gas from the Born-Haber cycle. So yeah, yep, that's supposed to be a gas. Okay, so now for our formation equation, we can't use sodium gas. We need solid sodium. Okay, so there's our solid and sodium gas, because again, we need sodium gas on the right to cancel out sodium gas on the left. And what's this one? Here's 7. Okay, so like Hess's law, we're going to add all these up. Okay, so that's going to give me sodium ions, my chloride ions, atomized sodium, atomized chlorine, an electron, my chlorine gas, which is my standard elemental form. Because again, remember, the formation equation can only use standard elemental forms and produce 1 mole of the final product. And then my standard elemental form of sodium. That's on the other side. What I'm trying to produce, the 1 mole, sodium chloride. And then sodium ions, electron, chloride ions, atomized chlorine, atomized sodium. And so then we say, well, what's the same? So electrons will cancel, chlorides will cancel, atomized chlorine will cancel, sodium ions will cancel, atomized sodium will cancel, and what we're left with so as we did earlier, we just used we used Hess's law to figure out the overall reaction that's occurring, and that's the formation of sodium chloride in its formation equation. Okay, so since we have that now, we use Hess's law to add together all of these enthalpies. So see, that'll give us our lattice energy. That's 496 minus 349 plus 122 plus 107. And we remember that the whole thing is a negative 411 from our Born-Haber cycle. Okay, well, we don't know lattice energy. So when we solve for lattice energy, minus 411 minus 496 plus 349 minus 122 plus 107. Our lattice energy comes out to be a negative oh, that's minus 107. Minus. There we go. Negative 787 kilojoules per mole. So that's using Hess's law, given the fact that we have to know that equation right there, which is the equation we have to have for lattice energy. Again, ion and gaseous form plus ion and gaseous form gives our crystal. And we're then trying to find the overall reaction, which is the formation equation. Another way we could do this is we could say, well, all right, plenty of space. Well, we know the overall reaction. And we're trying to work our way towards finding the lattice energy equation. Okay, so we go back up and we look at all of these, okay? So these are where I'm going to be getting everything else from. I'm just going to be putting them in a way that will get us where we need to go. So, like for example, you notice I have 1/2 Cl2 gas on the left. I actually need to get 1/2 Cl2 gas on the right now. So that means I'm going to take this equation, the atomization, and if you look, so here, that's this equation, but I flipped it. So you remember if I flip it, that means I'm going to change the sign on this delta H. Okay, now I know that my lattice energy equation has to have chloride ions. On the left, I need to get rid of atomized chlorine on the right. So we will use the electron affinity for chlorine. Okay, so let's take a look at this. So again, we flipped it, so we changed the sign. Okay, now we will use the electron affinity for, let's see, because that is going to give us sodium ions. We left that one the way it was, so that's going to be a negative. Did we leave it the way it was? Nope, we actually flipped it. So again, we're going to change the sign to negative 496 kilojoules per mole. And then we need to get rid of the sodium gas, and we need to get rid of the solid sodium. So we're going to flip the atomization of sodium equation, changing its sign. So now we're going to add everything together. So sodium chloride. And let's see what we have. Okay, so solid sodium's gone, 1/2 Cl2 is gone, chlorine gas is gone, electron is gone, sodium gas is gone, and I end up with the lattice energy equation that I need. And I use this method this time because now I'm not going to have to solve for the lattice energy. I can just use Hess's law to straight add up all these delta H's, and it will give me the lattice energy. And so once again, we have the lattice energy of sodium chloride. And again, you can use Hess's law to figure out the overall reaction, but then you'll have to solve for the lattice energy. Or you can take the individual steps of the Born-Haber cycle and put them together in a way that's going to yield the proper lattice energy equation. And then you just straight add together the column of enthalpies and you'll get the same answer. But when we're looking at lattice energies, so again, we're back to Coulomb's law here. And here we have some some ionic radii. But let's take a look. Like if you look at KBr, so potassium bromide, you notice its lattice energy is 682. Let's think about that. So your Ke is your Coulomb's constant. We don't need to worry about that. We're just thinking about this in terms of proportionality. So your KBr is going to be, your charges are +1, -1. So it's +1 times -1. And then your R, so your, let's see, that's going to be R 152 plus 182 equals 334 picometers, uh, versus the R for, let's say, beryllium oxide versus, so that'll be an R of 185 picometers. Whoopsies, what am I doing? And the charges for beryllium oxide are +2, -2. So in the potassium bromide, we're multiplying together +1, -1 and dividing by a larger R, versus beryllium oxide, we're multiplying together +2, -2 and dividing by a smaller R. So that shows you why the lattice energy for beryllium oxide is going to be so much larger than the lattice energy for potassium bromide. So now we're going to talk about finding the change in enthalpy of a reaction by looking at the covalent bonds involved in the reaction. And we have an equation very similar to the delta H we used when we were talking about enthalpies of formation. Only this time, you're looking at the energy of the bonds that are broken minus the energy of the bonds that are formed. Your value of N is number of moles of a certain type of bond, and your bonds broken is a positive term because energy has to be put into the system to break bonds. Your bonds formed is a negative term because when bonds are formed, energy is released. We're also going to be working with different types of bonds now. So when we say bond type, like a CH bond is a type of bond, an OC bond is a type of bond, so on and so forth. And we'll also have single, double, and triple bonds. So let's just look at a reaction and work on figuring this out. We have methanol plus carbon monoxide is going to yield acetic acid. Okay, so we need to really break this down and say, well, what bonds are broken? What's formed? So acetic acid, well, not yet. Methanol is that. Carbon monoxide is a triple bond. And then our acetic acid, we're going to have our methyl group. And then we're going to have our carboxylic group. Okay, now we say what was broken, what was formed. Okay, so to be able to get the CC bond, that CO bond is broken. You notice on the right side, I have an OH, so my OH bond's not broken, but I need to use the carbon monoxide, so this triple bond is going to be broken. And then what's formed? A carbon-carbon bond is formed. A CO double bond is formed, and a CO bond is formed. So that's what we have to take account of. Okay, so delta H is what? And then I'm going to, I use my table here. I'm going to say, well, a CO single bond 358 kilojoules per mole. And how many moles of this? I have 1 mole broken, 1 mole formed. Let's see, my CO triple bond, 1072 kilojoules per mole. And I have 1 mole broken. The CC bond, it's 347 kilojoules per mole. I have 1 mole formed. And a CO double bond, 745 kilojoules per mole. And I have 1 mole formed. Okay, so my theorem bond energy for the broken bonds minus the total bond energy for the formed bonds. Okay, so when I take all the numbers I just brought down, 1 mole times 3, that is going to be the broken CO bond, plus 1 mole times 1072 for the broken CO triple bond, minus 1 mole times 745. And that's going to be the formed CO double bond, plus 1 mole, 347. That is the formed carbon-carbon bond, plus 1 mole, 358. And that's again, that's going to be the formed CO single bond. And when I add all this up, I am going to get, oops, negative 20 kilojoules as my estimated change in enthalpy. Now, where'd the kilojoules per mole go? Well, I take number of moles times bond energy, that's going to give me mole times kilojoules per mole equals kilojoules. So I'm just multiplying it out. Okay, so that's going to get us through what we need to get through today, and we'll pick it up again tomorrow. So I will talk to you later.